In this video, we'll learn how we can implement multiple linear regression using gradient descent algorithm. So in the previous video, we'll learn about multiple linear regression, and we also discussed about the gradient descent algorithm in great depth. So in this video, we'll work with a dataset. So let me first introduce you to the dataset that we will be working with. Now the data that we are given is about computer hardware attributes. And using those hardware attributes, we are supposed to estimate the relative performance of your CPU. Now the predictors that we are going to work with are, first is this. This represents the machine cycle time in nanoseconds, and all the values vertically down from this represents machine cycle time in nanoseconds. Then we have the minimum main memory in kilobytes, maximum main memory in kilobytes, cache memory in kilobytes, minimum channels in units, then we have maximum channels in units, and the following attribute, which is this one, is your output or target variable, which is the published relative performance that we want to predict using the multiple linear regression algorithm. So now let us start writing some code for this to implement multiple linear regression on this algorithm, because we can see we are having a collection of predictors. So we are having more than one parameters of our model. So we will be using multiple linear regression to handle this, because it is not a simple linear regression case. And we will optimize it using gradient descent algorithm. So let us see how we can implement this. So first I will import the required libraries. So import the required libraries. First let us import all the packages. So import CSV, import numpy as np, import scipy as sp, import matplotlib, and then from matplotlib import pyplot as plt. So now let us define a method to basically read the entire dataset that we are having. So we'll go to the file path, which is the dataset.csv file, and we will be reading the dataset row by row and collect the data that we are getting for the predictors and the output response variable, which is the performance that we are trying to predict. And we will use the output variable as a label because here we are dealing with supervised learning. So let me leave a docstring comment here, and I will say reading the dataset. So I'll define a method and I will name it as getData, and I will pass a file path to this. So first what we need to do is, using the open method, we'll first read a file in the read mode, and this will give us a file instance which we can use to read and manipulate the content of the file. So I can say file equals to, and I will use the open method that will give us a file instance, and it will return a string. So the file can either be a text or a byte string, but in this case we are using a CSV file. So I can pass on the file path that we get as an argument in the getData function, and I will use the read mode for reading the file or for reading the entire dataset row by row. Now for collecting our predictor collection, because here we are gonna have 6 predictors that we'll be working with, and this is your output performance that we want to predict. So to collect the predictors, I will be using 6 variables. So I will say x1 and set that to an empty list, x2 set that to an empty list, x3 set that to an empty list, x4, x5, x6. So first here we will take on the machine cycle time in nanoseconds. Then here we will collect the minimum main memory in kilobytes, minimum main memory in kilobytes, then maximum main memory in kilobytes, then cache memory in kilobytes, minimum channels in units, maximum channels in units. So now we need the output response variable, So I can leave a comment down here, Predictor Collection, and down here I can leave a comment, output response variable. So for that I will define a variable y and set that to an empty list, published relative performance. So published relative performance of the CPU, which will be an integer. So now let us set up a CSV reader on the file object so that later you can iterate over the rows present in our dataset. So I will say reader CSV dot reader, and I'll pass on the file instance that we got from the open method. So now let us write a simple for loop to iterate over the file on which we have set up a reader, which will help us in reading the entire file, and then we'll omit the commas, and it will omit the commas by default for us so that we can easily grab those values without having to deal with the commas. So right on line number 27 I can make a loop and say for row in reader. So we are going to loop over the entire dataset row by row. So first this row, then row number second, row number third, row number 4, and so on, and we are having a total of 209 rows to deal with. So what we need to do is that for each row we want the value of our predictors. So first from each row we'll grab the first predictor like this. So suppose we are on the first row, so the temporary variable will be set to this row, and we will grab all the values for our predictor for the very first data point, which is represented by row number 1. So for each row you want the value of predictors. So for the very first predictor, which is present at index 2, which is 125, we'll grab that, we'll add that to x1, grab this, which is the second predictor, add that to x2, this will go to x3, x4, x5, x6, and this is your output performance that you want to predict for a unforeseen data point that we will pass when we will implement that functionality. But for now we will be using the output performance as a label for our predictions or for training our model. And for each row we will repeat this process. We will grab all the predictors, we will append them to respective variables that we have declared, which are those x variables, and we will append the label into the y variable. For each row we will iteratively do that process using a for loop. I can say x1 dot append, and what we need to do is we need to grab the very first predictor which is present at index 2 for the very first row that we are currently on. And once we have dealt with the row 1, we will go to the second row, we'll go to the third row until all the data set is completely done. So row 2, and then what I can do is I can copy this and paste it multiple times. And for getting the second predictor, I will get that from row 3. So suppose this is your current row that you're working on. So row 3 will represent 256, and this will go to x2. Then row 4 will be this, row 5 will be this, row 6 will be this, row 7 will be this, which will go to x6, and this will go to y, because this is your label that we will use for training. And we are going to grab all these values for each of the rows. So here row is a temporary variable that we are using, this row, and each time it will refer to a different row. So once the entire loop is done, you will move forward to the second row of your dataset. Once this row is dealt with, you will move forward to the third row, and so on and so forth. x2 dot append float row 3, and then so this is how we got all the values for our predictors once the loop is done with. And finally the output response variable, which will make use of as a label for our learning process, because we know that here we are dealing with supervised learning, and I already told you in the initial videos of this series that supervised learning will require labels for training your model. So for getting those labels, for each row we will require this value, which is the second last value of a particular row. For each row we want these values, and we will append these values into the variable y using our same for loop. So we are inside the for loop, and I will say float row 8. So this way you will be able to get the value of predictors and the output variable from each row iteratively using the for loop. Now once the loop is done, we will have the complete collection of predictors, wherein each predictor as well as the label will have 209 values, because we are having 209 data points in our dataset. So now we have tapped all the values for our predictors and the response variable from the dataset. So now we can safely close the file in order to prevent any memory leak. Down below, outside the for loop, I will say file.close, and then let us return the collection of predictors. So I will return an array, and inside the array I will return a collection of predictors. So np.array x1. So for all the x's we will be returning a two-dimensional list, as you can see, because this is your outer wrapper, and inside this we will be passing on each predictor array, which is itself having bunch of values. Each will be having 209 values for your predictor, for your specific predictor. So for your x1 predictor, you will have all the 209 values in your vertical column representing x1, means representing the machine cycle time in nanoseconds, and so on for all the predictors. So np.array x2, np.array x3, np.array x4, np.array x5, np.array x6, and then here we will say np.array the response variable or your target variable. So this is the entire implementation for getting our data from our dataset. So now what I can do is, down below I can say I can invoke the function, and we'll get the predictors collection, which is x, and the output target variable, which is y. So get data, so we can say dataset.csv, and once we get the data we can print that to our terminal, so print x and y. So let us try the code now. I can say python mlrgb.py press enter. Now you can see we are getting all the values for predictors and our label, which is the output variable. So for each predictor we will be having 209 values, and for the label, which is the output variable, we will also have 209 values. So this was the implementation for reading our dataset. So let us move on to implement the gradient descent algorithm. So I'll leave a docstring comment here, and I will say gradient descent algorithm implementation for our dataset. So I will say a function gradient descent algorithm, and it will receive the predictors collection, the collection of response variable, and the learning rate. So we have already discussed about the gradient descent algorithm in great depth. If you haven't watched that video, the link for that can be found down below. So let us leave a print statement, and I will say training multiple linear regression model using gradient descent. So now let us define a variable for maximum iterations that we want for our gradient descent algorithm to run before it converges to give us optimal values of m. We have already discussed in detail about gradient descent algorithm and multiple linear regression in the previous video, so don't forget to check that out. The link for that is of course down below. So I will define a variable maximum iterations that we want. So I will set that to 4000. Now this boolean will let the program know whether the gradient descent algorithm has reached its convergence state, which means whether the algorithm was able to find the local minima where the slope of your residual sum of squares with respect to your parameters, which in this case are multiple, is 0. So now let us define a boolean which will help us identify whether our algorithm has attained convergence or not. So in the converged state, we know from the previous video that we will get a line that is parallel to our x-axis. So an optimal value of our model parameter will be obtained at that stage, and the slope of RSS in that case is 0. So I will name it as has converged. So has converged, and set that to false. Now let us define a variable rows count to store the number of data points that are there in the current dataset provided for training. So I will say rows count, set that to x, which is the predictor's collection, and we'll grab the very first row and check the shape for it, which will return us the number of rows that you will have in your dataset. So now let us define some initial values for our model parameters. Here we will be having 6 model parameters as per the equation of multiple linear regression, which I discussed in the previous video. So set them all to 0. So I can say m and set that to 0, 0, 0, 6 zeros. Now what you need to do is we need to compute the initial value for error based on the initial model parameters array that I just defined above. So I will say error, and I will invoke the RSS function that we will define in just a minute, and I will pass on the predictor's collection, the response variable collection, and the model parameters, which is the assumed one that we have taken here on line number 52. So we're currently setting them to all zeros. So this will be our initial value of error. So now let us print the initial value of our error. So I will say print initial value of RSS, or you can say the cost function. What we need to do is we need to define a loop and compute the value of our gradients one by one iteratively. Because we are having 6 model parameters, we will be able to compute 6 gradients, and we will be working along various dimensions and not just in a single dimension as in the case that we had discussed in the previous video. So we have to apply the gradient descent algorithm along multiple dimensions, because here we are having more than one model parameter or more than one coefficients for our model. So I will set I as 0, and I will say while we haven't attained the convergence. So I will say while not has converged. Now for each training sample we have to compute the gradient, which is the partial derivative that we had seen in the previous video. So I can say g0, which is the gradient of 0, and 1.0 in the float terms by rows count. So whatever number of rows we are having in our dataset, and multiply that with, so we need the sum, and for all the values what we need to do is we need to calculate the predicted value for a specific row, and for each row in the dataset we have to compute the gradient 0, and successively we will be computing all the gradients, the 6 gradients for our dataset for our problem based on multiple linear regression, where we are having 6 model parameters. So in just a minute I will be defining a method which is predicted value for a specific row, and it will take on our predictors collection, the row we are currently looking for, which is the ith row, and we will pass on the model parameters, and then we will take on the actual value. So predicted value minus actual value, we'll sum that up over all the dataset. We'll sum up the difference between the predicted value and the actual value, and we will use list comprehension here for I in range to rows count. So we'll be dealing with all the rows and we'll be computing this value, and this will give us the gradient of 0. Now let us copy this and let us define gradient of 1. So g1, 1 upon the rows count into the sum of the differences for the predicted value for your ith row minus the actual value, and then here we need to multiply the very first predictor, then copy this. Now we will consider the second predictor, and this I will basically loop over all the values that are there in the second predictor. So like this. So this is your second predictor, and this is represented by x1, and then if you say x1i, and I is varying from 0 to 209 because we are having 209 data points, you'll get all these values. So x1 of 0 is this, x1 of 1, x1 of 2, and so on for all the columns. You will be getting these values. Okay, so this will give us gradient of 2, and then here we can copy this out. Now we can compute the gradient of 3 based on our predictor, which is the third predictor, x2 and I. This is your x2, and all the values below it is x2. So x2 of 0 is this, x2 of 1, x2 of 2, and so on. And we are looping over all the rows that are there in our dataset by saying for I in range rows count. And let us do this a bit quickly. So I will copy this out. So now we will get G4, gradient 4, and I will say x3 of I, and here for G5 we'll have x4 of I, and for G6 x5 of I. Okay, so this is how we can compute the gradients along various dimensions. So once we get all the values for our gradients, we'll get some temporary values for our model parameters. So let us set them using some temporary variables, and then we will simultaneously update our collection of model parameters that we assumed initially as all zeros. So I can say temp 0, and we will use the equation that we had discussed in the previous video. So I can say m of 0, I will take on the very first value of our model parameter, and I will subtract the learning rate, multiply that with G0. So this will give us the temporary value of our parameter of our model, the very first parameter of our model, which is temp 0 for now. So temp 1, m1 minus the learning rate into G1, and let us copy this 4 times. So temp 2, 3, 4, 5, and take this as m2, m3, m4, m5. We'll require one more model parameter, so I missed a 0 here. Let us change this to G2, G3, G4, and G5, and we need one more. Change this to G6 and M6, and this will be temp 6. So now we have the new values of our model parameters in our temp variables. Now let us update our model parameters in the actual list which we defined for it. So I can say m0 and set that to the temporary variable, that the temporary value for our model parameter that we obtain after the very first iteration of the process. Okay, so I can say temp 0, then m1 will be temp 1, and the whole loop will continue. This loop will continue until we get to convergence, where we get the optimal values for all our parameters, which are m0, m1, m2, and all those 7 parameters. So m4, temp of 4, m5, temp 5, and m6, temp 6. So now we have the new values for our model parameters. Let us again try to compute the RSS error by passing along with the predictors collection and the response variable our list of the new model parameters which we get after the very first iteration. Okay, so for each successive iteration we will be getting the updated values of our model parameters, and we will continue getting them until we reach the convergence state. So this is how you will get the optimal values of your model parameters. So I can compute the current error, and I will use the RSS function which we will define in just a minute. So x, y, and our model parameters, which is the updated one. And with each iteration you will be getting new values for all our model parameters. Okay, so this is the process that we are following here. Now if your I, if I take a modulo with 250, if this comes out to be 0, you can print iteration I plus 1 current value of RSS cost function based on updated values of m parameters or your model parameters, and I can say current error And after that, what we can do is we can update our error with the current error, and then we can increment I by 1. Now what will happen is if I reaches out and becomes equal to our maximum iterations, because you know that I represents your iteration count, and if it becomes equal to our maximum number of iterations, then only we will set the has converged boolean to true, and whatever optimal values you get for the model parameters at that point of time, we'll consider that as our optimal collection of our model parameters. Though you can self-tune the value of our maximum iterations according to your needs, but I'm taking a value of 4000 as of now. So as a side note, if you increase the value of your maximum iterations, it will take more time to get to an optimal value for all our model parameters. So for defining that convergence point, I will say if I reaches the maximum iterations, which is 4000, I will say print training process halted. So here we will halt our training process as maximum as number of iterations maxed out. For breaking out of the loop, we can set has converged to true, and now whatever values of model parameters we will have, we will use them for our multiple linear regression analysis that we will do in the code that we will write later. So now let us return the list of our optimal model parameters that we computed above. Let us try this. This will not work as of now because we have to define the function for predicting the value for a specific row. So let us do that. So now let us define the function for computing the residual sum of square error function to compute the value of RSS. So I can say def RSS, and this will take on our predictors collection, the response variable collection or your target variable, which will serve as a label, and your model parameters. So this will help us in computing the error right before we start with our gradient descent iterations and at the point when we require them. So at this stage we will also require to compute RSS, and we will update our error, and we will advance one iteration, and then if the iterations max out, then we will converge, and this will be here. So back here we define the method for RSS. So let us define a variable called as temp and set that to 0, and what I will do is I will iterate over all the rows that we are having in our dataset. So I can say x0 dot shape, so this will give us the count of the rows, and dot shape 0, and then for each row we will have to compute the predicted value. Okay, so if I go back to the dataset, I will be using these values. This will be x0, so x will have all the predictor values. So this is your first predictor, and all the values below it represent the first predictor collection, second predictor collection, this and all below it, third predictor collection, this and all below it, and all these collections are wrapped inside an array. So it's a two-dimensional list. For referring them, we will have to use one more index or one more index to grab these values, and then we can get the predicted value based on our dataset. Okay, and the actual value you will get from this, which is your target or your response variable, and then we can take a difference of that and raise that to the power of 2 to compute the value for your RSS, which we have discussed already in the previous videos. So let us define a variable predicted value, and I can say m0, which is the first model parameter, plus m1 into x0, which refers to our very first predictor collection. So this refers to a list. Okay, but if you want to, because we are having a 2D list, so in the 2D list if you say x0, then you will refer the innermost list, the first list. This will refer to the first list in the 2D list that you're having, and then for grabbing the values you can use another index I, and you will successively grab the values for predictors. So if I say x0i, this will refer to this x0i, I. So this is our very first predictor, and if I say x0, 0, this will refer to this, x0 and 1. So we are saying that in your predictor collection, I'm interested in getting the second value, which is this x01, then x02, x03, and if I say x10, this will be this, so x10, because this is our second predictor collection, and second predictor collection is represented by this value and all the values below it. So x10, x11, x12, x20, and similarly if I talk about this, it is x30 and this is x31, x41, x51, and then I can say plus m2 into x1I plus m3 into x2I plus m4 into x3I plus m5 into x4I and m6 x5I. So for the very first row, we will be getting all the values which are these. Okay, so this is x00, x10, x20, x30, x40, x50. So in that case, you can assume I to be 0, and when I will change, when the loop will go in the second iteration, you will have x01, x11, and in that case you will have these values, x01, x11, x21, x31, x41, x51. And when you move further, to get all these values, you will put them in the equation of multiple linear regression. You will get a predicted value for all the rows one by one. Okay, because we are following the process iteratively, and once you have the predicted value, getting the actual value is very simple. So you can say actual value. For that I can say y of I. So if I say y of I, y is represented by these values. So this particular column 198, 269, the second last column. Okay, and if you want to refer to these values, you will use the same index. You can say y0 is this, y1 is this, y2 is this, and these are your actual values, which are your labels. You can get the actual value, and for getting the RSS value, so for temporary sake, because we'll be getting the final value once we completely iterate over the data set that we are having. So temp is temp plus predicted value minus actual, and raise that to the power of 2, and then come out of the loop and return, so np dot square root. So we'll take the square root of the temporary value that we are having, which is our final value, because once the loop is done, we get the final value for your RSS. And we can say x0 dot the number of rows that we are having in our data set, or number of data points that we are having. Now we have written the function for RSS. Let us define the function for predicted value for specific row, which we will be using here when we were computing the gradient iteratively till we reach convergence. So let us go above, and right below our RSS function, I can say def predicted value for specific row, and I can pass on the predictors collection specific row that we are using here, and then we can pass on the model parameters, and then I can say return, and for the predicted value we can use exact same expression as this one. And let us copy this and paste it down below, and this will be our predicted value for specific row. Once you go down below here, you'll have the predicted value for specific row, and then the actual value you are getting from the label for each row. And with this loop, you are looping over the entire data set. Okay, so you are computing the gradient 0, and successively you are computing all these gradients as well using the same concept. So once you got the temporary values of your model parameters, you successively update your original collection of model parameters, which is represented by m, and then you will again compute the error, which is the residual sum of square error, and here you will update the error. And once you max out, convergence comes and the process stops. Let us try to call our function gradient descent algorithm and pass on x, y, and the learning rate. So now let us use the optimal value of the learning rate and pass it here. So I'm taking this as the value for learning rate, and then you will get the coefficients or your model parameters because we are returning them here, the optimal collection of model parameters, and then we can log the coefficients on the console. So let us now see whether whatever code we have written till now works fine or not. So I will go here and say python mlr gb.py. See, it says training multiple linear regression model using gradient descent. Initial value of RSS you are getting here. Then iteration 1, the current value of RSS based on updated values of model parameters. And then with a step size of this 250, we are seeing that the value for our model parameters, and this is running and it will converge when you max out. So when your iterations will reach a count of 4000. So it is still running 3001. And finally it says training process halted as number of iterations maxed out. So these are your values for model parameters, and as you can see we are getting negative values as well. So this is your M0, this is your M1, M2, M3, M4, 5 and 6. So we are getting all the 7 coefficients, or you can say parameters of your model, by using gradient descent algorithm. Now we are done with our gradient descent algorithm completely. Let us define a method to make predictions for unforeseen data points. Let us say making predictions. Let us go here and make a print statement and say the final value of our model parameters are, and here we can say print prediction, and we'll pass on a 2-dimensional list of our data points, and each data point is represented by a list. So here we are having a list of lists. So do remember this, because this will help you understand the for loop that we will be using for making our predictions. Okay, both these data points that are represented by a list. So here we will pass on our values for our 6 predictors that we're having. So x0, x1, x2, and 0, 1 and 2. And then let us take a value of 300, 432, 3400, 3, 2 and 6. So now let us go right above and define a method to predict output variable y for new values of x using the estimated parameters of our model that we obtained and which is stored in the coefficients variable, which is right on line number 118. And this method can predict the output variable for single as well as a list of values of x, and each value is a list in itself, as I told you. So if only a single numerical value or a single list is passed inside that predictors collection, that will denote a single data point. So it will return the prediction for that very single data point. Otherwise, if you have a collection of different values, that is a collection of different lists, that means a collection of different data points in form of a list is passed, it will return us a list of predictions for each data point, and each data point, remember here that it is represented by a list, making predictions. So def predict and pass on the coefficients that we just got and passed on the predictors collection. So a predictors collection is a list of lists. If we are passing multiple rows, so suppose here we are passing 2 rows, each data point or row is represented by a list. But if you are passing a single data point, which is this one, and some values here, then this is a list of list as well. But here you are having only a single data point. Okay, so do remember this. So now what we need to do is we need to grab the values for model parameters in separate variables from the list of coefficients that we obtained after the application of gradient descent algorithm. So I can say m0 and set that to coefficients of 0, m1 coefficients of 1, m2 coefficients of 2, m3 coefficients of 3, m4 the coefficients of 4, m5 coefficients 5, and m6, which is the last model parameter or your coefficients 6. So now let us define an array for our predictions. So set that to an empty list. Now we need to check whether our list contains more than one data point or a single data point. And remember that each data point is represented by a list. So in any case we will have a list of lists, but we need to check whether our list contains multiple data points or a single data point. We need to check whether the x given to us is a list of multiple values or multiple data points. So if the length of our x, which is a two-dimensional list, okay, it is greater than 1, that means you are having more than one data points in your list. Okay, so this is the case I'm talking about, or I'm checking for, and here you will have all the values, all the 6 values for your x values, which is your predictor's value. But here we are given the values. Okay, so these are the values for the very first point for which we have to make a prediction, and this is for the second point where we are given the predictors. So we are passing that here, and then we are checking whether we are having a single point or more than one point. So here we are having more than one point. Okay, but had it been this, then it's a single point. Okay, so for the case of more than one data point, we can iterate over our predictors collection, which is this, and then I can say for x in x. So this complete thing is your capital X, and this represents small x, or your first data point. So this value is your first data point, this value is your second data point, and we are picking these first. So for x in x, and then we can make the predictions, and we can append a prediction. So for the very first list that you will get these values, we'll first focus on this list, and once this is done, once the prediction for this list is done, then we will move forward with this list, and once this is done, this loop will be done and we will come out of the loop. Let us make the prediction by using the multiple linear regression model, m0 plus m1 into x of 0, not capital X, small x. So x of 0, we're grabbing the first value for the list that you're currently on. So we are currently on this list, which is represented by small x. So small x0 will be this, small x1 will be this, 1000, small x2 is 3000, small x3 0, small x4 1, small x5 2. So we are using these values. Once we made the prediction, we'll move forward to the next data point if we have one, plus m2 into x1 plus m3 into x2 plus m4 into x3 plus m5 into x4 plus m6 into x5, not m6, m6, like this. And finally we can return the predictions here. Now if we come out of this, this means that we were having only a single data point in our collection of predictors that we have just passed, for which we want to predict. So if you have a single data point like this and no more list inside the outer list, so for single data point we can do is we can say small x and we can just grab that list. So if we have something like this, and here we have some values like this, so we'll take out this thing. Okay, so this thing will be your x0 in the case when you are having only a single data point, we can again make the prediction by saying y is equals to, so capital Y, you can say m0 plus m1 into small x, which represents your list, the list within the predictors collection, which is capital X. And since we are having only one data point, we can say x of 0 for the very first value, m2 into x1, m3 into x2, m4 into x3, m5 into x4, and then m6 into x5. And finally, you make a prediction for a single data point, and then you can return y. So let us correct this out. We'll pass a predict method here, and here you will pass on the coefficients, and then your predictors collection. So let us try the coding. Now you can see we are getting the value of predictions for the values that we passed on. So for the first hardware that we passed on, that is represented by these input variables, we are getting the performance to be 32.31, and for the second hardware that we passed on here, we are getting the performance as 27.8, which is a relatively low performance. So now let us do the performance evaluation of our multiple linear regression model. So let me leave a docstring comment here, and I will say performance evaluation of multiple linear regression model. So let us leave a print statement, new lines, and accuracy metrics of the model. And now we need to calculate RSE to compute the value of residual standard error for our implementation. Let us write down some code for that. So I will say RSS and set that to 0, and then what we need to do is we need to take the transpose of the predictors for each row in X. So we have the X, which is predictors collection, and in that predictors collection we are having a list of predictors and the values that they have. So the rows will get converted to columns, and columns will get converted to rows using this transpose operation. So if you want to learn more about transpose in matrices, a link for an article on matrix transpose can be found down below. So what I will do is I will say x and np.transpose and pass on our predictors collection. This will return us the transpose of that matrix. And now I will use a for loop. So I will say for index in range 0, length of x, or your predictors collection. Use a colon and press enter. And now to get the actual value using the labels for our dataset that is given in our dataset in the form of your output response variable, which is the relative performance of CPU, which is also the target variable that we were predicting above. Actual value, and I will say y, and I will access the label, so y index, and make use of multiple linear regression model now to predict for the relative performance of CPU to get a predicted value. So I can say predicted value. I will use the predict method that we had earlier defined and pass on the coefficients that we computed, and then we need to pass on our predictors collection, and passing the predictors collection is simple. So we can say x index, I want to specifically slice out and pass on 0:6 because we are having 6 predictors. And then to get the value of RSS, we can say RSS is RSS plus actual value minus predicted value, and I will raise that to the power of 2. And this is something we have already done in the previous implementation on linear regression, so you must be familiar with the implementation. It is somewhat similar to that implementation. You can come out of the for loop, because now we have the value for RSS, which is our residual sum of squares error, and then we can compute the residual standard error. So I'll define a variable for that, and I can say numpy square root, and then I can say 1 upon float and x dot shape to get the number of data points that we have in a dataset minus 2. Then you can multiply the entire thing, but under the square root, with RSS that we just computed. So let us log out the residual standard error on the terminal. So residual standard error colon and RSE. And let us try the code. So I will go to my terminal. Here I can run the command python mlrgb.py, press enter. So you can see our iterations are running. So let me pause this for a minute and we get back to the final result. So our iterations are now over, and you can see the accuracy metrics for the model. So we just computed the residual standard error for our model, and this comes out to be 76.9. So now let us end the implementation for this project by computing the TSS value, and then we will be able to compute the R-squared value, which is TSS minus RSS upon TSS. And we have already discussed about the accuracy metrics and their formulas in the video on performance evaluation metrics for our regression model. So now let us compute the residual standard error over the average interval. So I will copy this out and I will say residual standard error over the average interval, and I can say I'll wrap this in parentheses and say RSE upon the mean value for our output response variable and multiply that with 100. This will give us the residual standard error over the average interval. And now let us do the second part for the evaluation metrics or the accuracy metrics, which is calculation of R-squared metric. So we can set up a variable TSS and set that to 0, and for index in range over the predictors collection we will be iterating, and then first I will compute the actual value just like the above code. So actual value will be y index, and then the TSS is, I will update TSS by saying TSS is TSS plus actual value, the mean of our output response variable. So it's actual value minus the mean of our response variable, and I will raise that to the power of 2. This we have already discussed in the video on performance evaluation metrics. So it's very important to check out those videos so that you can completely understand what is going on in this code. And then once the loop is done, you have the value for TSS, and we can easily compute the value for R-squared by saying R-squared is TSS minus RSS divided by TSS. So now let us log the R-squared value to the console. So the value for R-squared, so I will log R-squared to the console. So let us run the implementation and see the final value for R-squared. As you can see, now our iterations are running. So let this finish. So now our iterations are over. You can see we are getting the residual standard error over the average interval, which is 72.82, and the value for R-squared comes out to be 0.77. So this was all about the video on multiple linear regression implementation. So if you liked the video, do give it a thumbs up, subscribe to the channel, and I will see you guys in the very next video where I will be discussing about the performance evaluation metrics for the classification model. So let's catch up in the next video.